Or should I just start at 2:00?
People are just starting to.
Yeah, I see some participants.
Oh, yeah. So maybe we need to give a few minutes.
And I'll wait for your signal. Okay. Good afternoon. And also to those of you who are in China, good morning. And good evening to those of you in Lebanon or Greece. My name is Amar Chaker. I'm the director of the Engineering Mechanics Institute of ASCE, EMI. And I would like to take the next few minutes to give you some background, some context for today's event, which is the 2020 EMI Annual Objective Resilience Lecture, which is hosted virtually by the University of Mississippi, and it's a disaster resilience constellation. EMI is one of the 9 specialty institutes of ASCE that cover different areas such as transportation, structures, water resources. EMI is the smallest institute with only about 2,500 members. Nearly all of them are in academia or research, and some are in what I would call high-end engineering firms. EMI was established in 2007, and even though it is the smallest institute, it is very active and I would say quite successful. It has the Journal of Engineering Mechanics, which is a highly regarded, peer-reviewed monthly journal. And EMI also holds 2 conferences every year. One in the US, which is usually quite a large one. The last couple of years, we've had about 1,000 attendees, which is 40% of the membership, which is quite unusual. And then we also have an international conference, which has been alternating between Asia and Europe, where there's also quite a bit of activity in the area of applied mechanics, engineering mechanics. EMI is active with the journal, with conferences, and the engine that powers those activities are the 20 technical committees of EMI. The members review papers submitted for possible publication in the journal, about 700 to 800 every year. And they also organize sessions and mini symposia at the conference. Some of them, about half of the committees, organize student competitions. Some of them publish books or special issues of the journal. And one of these committees is the Objective Resilience Committee, which was established in 2005 following a proposal by Dr. Mohamed Touni, who is the current chair, has been the chair since then. That Objective Resilience Committee has been very active. It has over 50 members. Again, a large portion from academia and research, but also we have members from industry and from government agencies, which gives a special character to the committee. And the committee has been organizing sessions every year at the conferences, the EMI conferences, has been holding a student paper competition every year, has also held 2 workshops, one at the University of Mississippi, in Oxford, Mississippi, and one at Tongji University in Shanghai, China. The committee is also working on a large publication, a book which will be 4 volumes, I believe, which is in the last stages of review. It's going to be what is called a manual of practice, which goes through a very thorough review process and should be available, should be printed, published by ASCE next year, probably by early summer, hopefully. And one of the accomplishments of the Objective Resilience Committee is to establish this annual Objective Resilience Lecture. The first one was given in 2018 at the University of Michigan by Professor Paolo Gardoni of the University of Illinois at Urbana-Champaign. Last year, the Objective Resilience Lecture was given at Lehigh University by Professor Jamie Padgett of Rice University. And in a couple of minutes, we will have the pleasure of listening to Professor Yuri Bazilevs of the Brown University, who will be giving this year's Objective Resilience Lecture. At this point, I'd like to hand it over to Professor Chris Mullen, who will tell us more about the University of Mississippi, its disaster resilience constellation, and will introduce our speaker. Thank you.
Okay, well, thank you, Elmer. I first like to say a note of thanks to all the participants who've taken time to join us in this live webinar. We, of course, would have loved to have hosted everybody at the university in our campus in Oxford, Mississippi, but these are the times that we are in. And so we're pleased to be able to meet with y'all through this Zoom webinar. So I'd like to say a few words about why this lecture or where it fits in that series. First of all, I met the speaker at a conference in 2017. We both share an interest in the use of finite elements as a method of exploring behavior and structures and mechanics and fluids. And so as time proceeded and we've been having these prior lectures, I noticed that we've pretty much covered sort of the objectives and sort of the broad aspects of objective resilience and how it's implemented. And it's now quite mature, as Dr. Chaker mentioned, that we have a 4-volume set of research that is being brought into a manual practice at this point. So this year, when I was asked by Professor Atuni, who's the chair of the Objective Resilience Committee, to host this year's lecture and to select a lecturer, Yuri came immediately to mind in the sense that whereas in past we've talked about broader aspects, I think the key going forward and as represented in the manual practice, you'll see the technology and the tools are going to become key to advancing the state of practice and the state of the art in this area, in my opinion. And so I've gotten to know Yuri for a few activities that we've done together, and I see what he's doing as being at the forefront of some of that advancement of the technology, in this case, the simulation tools. There's plenty of work going on in the materials aspects and in the development of sensing technology. We actually held workshops on those topics at the University of Mississippi in prior years. But this year, I like to focus on the simulation, and Dr. Bazilevs, I believe, is a leader in that area. A few words about his, well, before I introduce him, I'm sorry, let me go ahead and if we could display the outline. We'll go over the pattern of this live webinar, since we don't have the luxury of doing that in person. So let me just say that thank you, Dr. Shaker, for the introduction and background to the series. I'm going to go ahead and introduce the speaker in a moment, and we will have a few words by Dr. Bazilevs live before the pre-recorded lecture is given that will last about 50 minutes. And as that lecture is given, I'm going to encourage all of the registrants to maybe make a mental note and put in the Q&A button any questions that you may have. We will have a live Q&A session after that recording, and so that will give you a chance to speak directly to Dr. Bazilevs. And I'll be making a tally of those as it goes along. So then we'll wrap up and with some acknowledgements and closure. So that's sort of the brief outline. I would like to say that Dr. Bazilevs has been an active researcher in this field, and both actually multidisciplinary. He's involved not only with the American Society of Civil Engineers, but also American Society of Mechanical Engineers, and in computer science fields. So he received the 2018 ASCE Walter Huber Research Prize. And he is the chair of the Applied Mechanics Division of ASME currently. I met him when he was co-chair of the 2017 EMI conference in San Diego, when he was at the University of California, San Diego. I'm going to go ahead now and let Dr. Bazilevs say a few words. Thank you so much for taking your time to do this.
Okay, thank you very much. Goes to Amar and Mohammed and you, Chris, for sort of placing faith in me and delivering this lecture. It's a big honor, and I do remember the San Diego conference very well and our interactions. You actually attended our computational fluid structure interaction course, and this is how it started. And I believe Amar was also a student in that class.
Yes.
So it's great to be able to talk about this this topic. And I guess without further ado, Kendra, please take it away. Okay, it's my pleasure to give the 2020 EMI Objective Resilience Lecture. I thank the organizers of this event and the EMI Objective Resilience Committee for inviting me to give this lecture. I'd like to speak about Advanced and Practical Fluid Structure Interaction, or FSI is the acronym, for large-scale structural systems. Before I begin, let me show you the following graphic, okay, that came out of a recent TEDx presentation that I've seen by behavioral economist Simon Sinek, titled "How Great Leaders Inspire Action." And so Simon Sinek tracked the way kind of companies communicate what they are and what their products are, right? And what he found is this inward mode of communication where they start with the question what, meaning what we do, right? Then they move on to how, meaning how they do it. And then the why comes last, where why is sort of something that answers the question why the customer should buy their product. Okay? An example of communication like this could be, we are a local company specializes in making sort of Italian style ice cream, gelato from natural ingredients. Okay, we source how, right? We source our ingredients from sort of local farms, and that gives them the necessary freshness for our product. And that is why our product is the best, and that is why you should buy our gelato, and which doesn't necessarily sound very convincing or special, okay? Then Simon Sinek investigated companies that are generally accepted to be very successful, okay? And what he found is that they communicate the research using the outward communication style, which is exactly the opposite, okay? They start with a question why, meaning why we do what we do, okay? Then they move on to how we do it, what is the secret sauce, right? And then what it is that they make, right? Becomes sort of the outcome of why and how. Of course, behavioral economists love to study companies like Apple, okay? Apple Inc. And basically the communication that you see from Apple is as follows, right? They start with a why, and they say that, you know, we believe in pushing the boundaries of what's technologically possible, what's possible from the standpoint of design and so forth. Their secret sauce, the why, is that you know, they try to hire the best people, put them in the working environments that inspire creativity and enables them to develop the best and most cutting edge and innovative technology. And that sort of, as a result, they sort of happen to make the best computers and devices in the world. And I think this is what resonates with a lot of consumers. And so the conclusion is the consumers don't buy what you do, but they buy why you do it. In other words, the underlying philosophy and belief system are important for creating a successful product. And so being inspired by this lecture, this TEDx lecture by Simon Sinek, I structured this presentation in the same way. So let me start with why, okay? Why we do what we do. Okay, so here are some general beliefs about advanced simulation, and we feel that advanced simulation is a cornerstone of engineering design and can thus affect and has been affected engineering in profound ways for decades. When it comes to the research and computational methods, and this is what we do in my group, we should constantly strive to challenge the status quo in the field, right? You all constantly strive for better methods and techniques, meaning something that's more accurate, faster, more robust, and etc. And again, this is more of a personal opinion. Computational methods research should be driven by advanced application, for example, design of next generation of long-span bridges, okay? Must be grounded in advanced theory, okay? So you bring in the right applicable mathematics, mechanics, computer science techniques, and should target specific challenges and be compatible with modern computing paradigms and platforms. Again, it's the expectation that you do things in the high performance computing environments today, take advantage of these things, okay? Now, maybe a couple of words about objective resilience. Is not exactly my field, but sort of I'm hoping to bring some of my perspectives on computational methods into the OR world, okay? And these are some of the objective resilience relevant beliefs, I feel, right? And kind of starting from the definition, when we talk about infrastructure or enterprise, right, it's referred to as resilient is if it's able to effectively anticipate, absorb, adapt to, and or rapidly recover from potentially disruptive events, okay? And so how do we achieve that resilience? Okay, the resilience, this may be achieved through, first of all, careful initial design when you anticipate such things, right? Once you've designed, you build your structure. I mean, it's important to continuously monitoring it and assess for things like damage and, you know, hopefully carry out some damage prognosis, which has some predictive flavor to it. Accurate prediction of future behaviors is very important if you want to continue, you know, making your structure resilient. And of course, targeted retrofitting to mitigate unforeseen events. Okay? And so as a result, in this case, modeling and simulation, and of course, we're talking about accurate, robust, and efficient methods, okay, plays a critical role on each one of the stages outlined before, right? Ensuring the desired resilience of a structural system. And again, mainly because of the large costs involved in carrying out experiments at full scale. Because, however, it is my view, and it's been my experience over the years, that experiments or observations should truly go hand in hand with the simulations wherever possible. Okay? So I mentioned applications and research driven by applications. Here are some of the interesting things that we're looking at. Wind energy, more recently in ocean and marine environments. We started developing air blast methods for demolition or retrofit. Biomechanics, especially the realm of biomedical devices, remains really important. And we also had some work in manned or unmanned aircraft and hopefully going into undersea vehicles soon. Okay, and so a lot of these phenomena require a careful job using methods for fluid mechanics, structural mechanics, solid mechanics, and their coupling. Okay, so let me proceed to the how of the presentation, and this is the so-called secret sauce. So how do we do it? Well, there are a couple of things that need to come together. And the first one is isogeometric analysis. Okay. The effort started a few years ago. The first paper appeared in 2005. So the biggest driver was Tom Hughes, University of Texas at Austin, and I was his first PhD student that defended on this topic. And sort of motivation for IGA came from the following chart that was provided by Sandia National Labs. Right? So if one thinks about an analysis sort of pipeline, right? You start by designing a solid model, okay? You create it, you need to carry out geometry decomposition, then you carry out the meshing, you manipulate the mesh, okay, to make sure that things are analysis suitable. You assign model parameters, assemble the model, and then you run the simulations, okay? So you post-process results and you archive the artifacts. Okay? And what you find is model building and analysis present a significant bottleneck, right? And amounts to 70-75% of your effort. And so we looked at the possible solutions, how to circumvent this. Okay? And this is how isogeometric analysis was born. Right? So we looked at the different fields like computer graphics and computer-aided design and what's done in those fields and how the geometries are represented. Okay, you see an example of a car modeled using surface splines. Okay, B-spline type technology. Okay, this is a cartoon character, and on the right you actually see very clearly the underlying surface spline mesh that it takes to model a character like that. Okay, this is a snapshot from a CAD software that makes use of what's called NURBS, not uniform rational B-splines, and over the years it's become sort of a gold standard in isogeometric analysis as well. Where you represent surfaces using this type of technology. And then finally, you see the use of splines and NURBS in architecture. This is a museum in art museum in Bilbao, where the drawings were designed using spline technology. So what we found is that splines are everywhere in the world except for in computational mechanics. And this was the birth of isogeometric analysis, where sort of over the years, we built an analysis framework, which is very similar to a finite element method in many ways, right? We make use of variational or weak formulations, and just sort of the underlying unknowns, okay, like displacements, temperatures, happen to be discretized by splines. And so the technologies that we use come from computer-aided design, computer graphics, and visualization. And the idea is that you have the same, in quotes, exact from the standpoint of CAD functional description that's used for the geometry definition as well as the simulation. Okay? And IGA certainly includes standard finite elements as a special case, but offers some other possibilities, such as precise and efficient geometric modeling, simplified mesh refinement once you've sort of built that initial geometric model, superior approximation of properties. Okay, these spline functions, even the rational counterparts of splines, are very good for numerical analysis. Okay, you're able to approximate things very well. Smooth basis functions. Okay, unlike standard finite elements, you are able to take derivatives, and these derivatives are continuous across element boundaries, and sort of that opened the door to a lot of different applications, especially in sort of the solids and structures arena, where, as you'll see later in this presentation, we take advantage of fairly kind of a new sort of shell technologies that are accurate and at the same time very efficient. Integration of design and analysis still remains a big area of research in IGA, and several groups are making a lot of strides on that, but I won't focus on it in this presentation. Okay. All right, so now the mechanics part, right? This is a engineering mechanics event, and there's no way that I can deliver a lecture in engineering mechanics without talking about weak or variational formulations, okay? So let me take you through kind of our thinking about fluid structure interaction, okay? And probably the details of some of these formulas are not so important, just the content and the philosophy that is, okay? And so we'll look at the problem from the standpoint of an augmented Lagrangian type approach, okay, where you identify, by U1 and P, it's done in the context of incompressible flows that can be expanded, designate sort of the unknowns that are coming from the fluid mechanics side, velocities, pressures. U2 are the unknowns coming from the solid, right, typical displacements or velocities. And then the way I couple the two subsystems, at least at the level of this augmented Lagrangian, is through a Lagrange multiplier type approach. Okay, so lambda is the Lagrange multiplier. And so the way I define the augmented Lagrangian is I take the contribution from the fluid, I add contributions from the solid or the structure. Okay, at this point they exist independently of each other, and then the way I couple them is through the Lagrange multiplier that enforces the kinematics of the fluid and the structure at the fluid structure interface. Note the subscript T here. That interface can be moving in time. Okay, very important. And then I add another term that's not usual in the Lagrangian approaches, but this is what sort of constitutes the augmented Lagrangian approach, is where I say I'm going to use sort of what I call a penalty parameter beta here. Okay, and the penalty parameter will bring the fluid and structural fields closer to each other. So basically, it will penalize the departure from the, basically penalize the error in the fluid and structural kinematic coupling. Okay? And so once I have the Lagrangian, I can start turning the crank. Okay, I compute the so-called stationary points of that Lagrangian by taking the variation of the expression on the previous page, that n, okay, with respect to fluid mechanics, structural mechanics, and Lagrange multiplier unknowns. Okay? And so what that gives me are three variational formulations, okay, that are coupled with each other. The top line here is fluid mechanics, okay? Right? You can see that the B's are the semi-linear form, kind of a linear functional, which are the loads, okay? And this term here is the effect of the Lagrange multiplier, okay? And this term here is the effect of this additional penalty that I'm bringing in, okay? The solid mechanics and structural mechanics is the same structure, right? You have some weak form or variational formulation governing the structure. Here's the effect of the Lagrangian multiplier, and here's the effect of the penalty, right? And the last equation just says in some weak fashion, okay, the kinematics between the fluid and the structure hold, okay? And so this is important, kind of a point of departure for a variety of, again, I haven't said anything about finite elements or discretizations, okay? The only constraint at this point is that I will treat both the fluid mechanics and structural mechanics in the weak form, which pushes me in the direction of using finite element methods or isogeometric methods or mesh-free methods, okay? So some of the more traditional finite difference or finite volume type approaches for fluid mechanics are unfortunately excluded from this framework. Okay? And so next is, can I do better? Okay, theoretically it's very good, but I really do not want to carry Lagrange multipliers with me. Okay? It makes things complicated, and it makes things fairly expensive from the computational point of view. And so the approach I take here is that first, right, as we all know, okay, Lagrange multipliers, right, when they penalize kinematic, kinematics, they take the interpretation of force, right, or in this continuum setting of the traction, okay? But now I have two subsystems that I'm coupling, fluid and solid, okay? So the Lagrange multiplier has the interpretation as a fluid traction with a solid traction, right? And because of the presence of these penalty terms, right, Lagrange multiplier also has this kind of contribution from the mismatch between the fluid and the structural kinematics. But if I subtract the two equations, right, I get this condition here, right? So independent of the presence of the Lagrange multiplier terms, the fluid and solid traction in this framework are always in balance. This is what you like to do. Okay? And so taking this as an expression, right, for the Lagrange multipliers, I can take a convex combination. I can take a variation of the Lagrange multiplier also with respect to the fluid mechanics and structural mechanics degree of freedom. And I can take this formulation and condense it to something like this, okay? So I basically analytically remove the Lagrange multipliers from the formulation, and I arrive at a fully coupled sort of fluid-solid system, okay? And so here, right, because the fluid mechanics and solid mechanics fields sort of exist independent of each other, I can discretize them, okay, independent of each other, okay? And then the coupling will take place over the interface that moves in time, okay, using these additional terms, right, that arise from the analytical elimination of the Lagrange multipliers. Okay? And so to me, this leads to an efficient fluid structure interaction framework that could lead to a lot of practical applications. One thing I'd like to note, these methods were developed for non-matching but conforming interfaces, right? You can think of two different meshes for the fluid and the structure, right? The meshes don't match at the interface, right? Because, structure could be more complicated, and in the fluid case, you may want to simplify things, right? But at least they're somewhat, conforming to each other, right? So as the structure moves through space, you're able to move the fluid mechanics mesh that follows it, okay? So in conforming in that sense, right? But there's been a lot of excitement in the community for the so-called immersed type methods, okay? And what happens is the formulation, as you see it, can actually be applied directly over immersed boundaries. Okay? And so when the structure is discretized using isogeometric analysis, we refer to this combination as the immersive geometric analysis, or RMGA. Okay? So I can set some coefficients, okay? And I find that if I look separately at the fluid mechanics and the structural mechanics problem, I see that I have a weak formulation of fluid mechanics that's driven by the structural kinematics, right, given here by U2, okay? And it amounts to what's called a weak enforcement, okay, of kinematic boundary conditions for fluids, which is really important, okay, in the setting, because I can control the extent to which I satisfy these kinematic conditions, right? And so if you work on sort of coarser meshes, you can relax the satisfaction of the slip component, right? Of the no slip component. You're allowing a relative slip between the fluid and the solid, and thus you don't need to employ very fine boundary layer meshes. Okay? When it comes to the structural mechanics or solid mechanics formulation, you see that it's driven by the traction coming from the fluid. Okay, it's becomes something very classical, but that traction is modified by a term, this penalty term, that takes into account the difference between the fluid and structural kinematics. Okay, So some special cases. Okay? If the meshes match, okay, I match the fluid and structural discretizations on two sides. All of these interface terms drop out, and I recover classical monolithic FSI. Okay. Another interesting thing is if I decide to approximate the fluid and structural solutions using the background mesh, okay, quantities, what happens is, again, the interface terms drop out, right? And you get an immersed finite element type approach. We'll show examples of that later in the presentation, okay? Next, if you decide to get rid of the fluid completely, okay, and just leave the solid, okay, and approximate it using the background discretization, you arrive at what's called a material point-like technique. So there are a lot of important special cases. Okay. Again, this was a fairly cursory overview, but I just wanted for everyone to get a flavor of how we think about FSI problems and what we do. Okay. Of course, there are a lot more details that goes into the decisions as to how to, how to stabilize the fluids, the choices of nonlinearities in the solid, how you want to approximate damage, how you want to approximate fracture, and so forth. But again, this overall framework allows you to plug in and remove the different. You kind of use your favorite, approaches for things. Okay. All right. So next is the outcome, the what. Okay. Hopefully, the why and the how is going to lead to a what that's significant. Okay, and so here I want a couple of cases that we covered over the years, right? And let me start with the work on the fluid structure interaction analysis of full-scale wind turbines. And here I'm listing collaborators, a lot of whom are my former students. They're faculty in other universities, as well as Sutana Sarkar, who's a real expert in stratified flows at UC San Diego. Okay. And the problem that we're after, right, is to be able to simulate scenarios like this. Okay, just like in this figure, it's been noticed that depending on the direction of the wind and how the turbines are placed, right, the turbines in the second row or third row start producing less and less electricity than the turbines in the first row. Okay, and certainly modeling can help understand that question. And so we abstracted our problem as follows, right? We're placing two turbines back to back, okay, that are separated by about 1 kilometer, right? All the dimensions are in meters, so there's about 1,000 meters, which is in between, right? So again, we're trying to solve things at full scale, okay? And the idea is to carry out a fluid structure interaction calculation, right, of this setup here, okay? But we have to do it in a way that's manageable and that is practical, okay? So what are some of the key ingredients that go into this calculation? First, let's talk about the structure, and this is where isogeometric analysis comes in, right? So while in these simulations, the tower is assumed to be rigid and stationary, the blades, right? First of all, the rotor spins, the blades spin, and they're able to generate deflections as well, right? So we treat it as such. The blades are actually complicated composite structures. And this is an example of a 10-meter Sandia CX100 blade that is a picture taken from a structural lab at UC San Diego. We actually got the blueprints for that, and with a complex distribution of the composite materials in different parts of the blade. Okay, and using ideas from isogeometric analysis, we actually built a geometrically exact model of that blade. We're able to distribute the composite parameters through the thickness, and we're comparing some of the natural frequencies, right, that are coming out of our model, right, compared to some of the frequencies obtained through full-scale laboratory testing of that blade, and the correspondence is quite good, both for the clamp case and the free case. When it comes to approximation of some of the lower modes, okay, like the first flapwise mode, second flapwise mode, first edgewise mode, and so forth. And that example was done a couple of years ago, around 2013 or so, but presents really a first validation of isogeometric methods in the full-scale structural setting. Okay, all right. So next, we're going to put our flexible blades into an FSI, into an FSI framework, right? And here, another challenge that needs to be addressed, right, is that the tower is stationary and the rotor is spinning. And so that's done, again, you using a formulation with two domains, okay? one domain moves, right? And the motion of the domain is dictated by the motion of the rotor, right? So there's a way to take a weak form of the fluid mechanics equations and put them on a moving domain using the arbitrary Lagrangian element formulation, okay? The domain around it contains a tower. There's no need for it to move, right? If it did move, then you have a problem with the tower, okay? And so that domain is stationary, right? But because of that rotational motion, right, we can actually, right, the interface between the two domains remains cylindrical, okay? And so the remaining challenge, right, is to be able to couple the two fluid mechanics solutions on the interface that is stationary and the interface that is moving, right? And again, it's done through some of those augmented Lagrangian ideas that allows you to couple discontinuous solutions, okay? Using this augmented Lagrangian approach, right, with an analytical elimination of Lagrange multipliers, okay? And so we did a test on a NREL phase 6 wind turbine rotor, right? This is sort of a test turbine. Each blade is about 5 meters long, okay? So it is full scale, but the scale is not big enough to generate it. So it's used for a lot of testing, right? And these are some of the snapshots of the calculation. You can see, right, with that approach, how the blade passes the tower, right? And then the corresponding changes in the aerodynamics, right? The sliding interface is somewhere between the blade and the tower, but you cannot really pick it up in the calculation, right? I like this slide a lot because this is the aerodynamic torque as a function of wind speed, right? Gray dots are the experimental data, right? And the curves are ALVMS calculations, right? Clearly, rotor-only calculation without a tower gets the overall torque, right? But it cannot capture the presence of the tower, right? You put the tower in, you get the red curve, right? Where you get a perfect dip in the torque following the experimental data, okay? So these techniques seem to work quite well. Okay? Now, you change the speed to 10 meters a second, you get a much bigger spread, right, in the experimental data. And now, you know, the location, right, where the rotor passes the tower is no longer visible, right? You can sort of pick it up, but it's not as pronounced as a 7 meter per second case. So there's quite complicated coupled sort of phenomena that are taking place that we're able to capture with these methods. Okay. So next step, right? Of course, when you go to the full scale, right, and these are rotors that are 300-400 feet in diameter, right? And you have a tower. And so every time you're looking at the wind, right, you cannot assume uniform airflow anymore. Okay? So in fact, these wind turbines operate in thermally stratified boundary layers. And so we teamed up with Sutana Sarkar and his students at UC San Diego to understand more about stratified flows. And we're able to take that formulation and actually put it on a moving domain, right? Because we need it on a moving domain in order to carry out the. So what you're seeing here is, right, a spinning cylinder, right, and a sort of a stratified boundary layer flow, right, where you see a very fast flow in the middle, right, sort of the so-called inversion layer, right, the boundary layer here, and sort of some modicum of turbulence around, right. This is a comparison of our moving domain model with that of Sutana Sarkar, and the average boundary layer for velocity and temperatures is represented quite well in our framework, right? And so now we have the ability to couple the fluid and the structure, right? We're able to carry out fluid mechanics on domains that spin and domains that are stationary, and by coupling the two, right? And then we're able to bring in atmospheric boundary layers into our fluids calculation. Okay? And now we're ready for a problem like this, right? And the way we're going to handle it is as follows. We'll break up our domain into 3 subdomains, okay? We first simulate the upstream turbine, right? Collect the velocity on the plane close to the turbine itself, okay? Impose it as an inflow condition on the intermediate domain, right? So here we just need to go and kind of transfer all this flow into the into the turbine in the back, right? Collect the velocity at the outflow plane and impose it as inflow boundary conditions. So again, nothing too complicated here, right? It's just we got to watch 2 things. Right. So upstream turbine inlet and all lateral boundaries, right? The velocity boundary conditions come from a standalone ABL formulation, right? That's computed by sort of a Sutano-Sarkar's finite volume code. Okay? And these conditions are imposed everywhere on the sides of the computational domain. Okay. Another important thing is because you do have this thermal stratification, you no longer have a uniform pressure on the outlet. Okay. So the pressure does take on a certain profile. Okay. You can compute what that profile is. Okay. From this the first simulation, then you need to take that and apply it as an outlet boundary condition in every one of the domains, right? To make sure you sort of guide the flow from one domain to the other without any dispersion. Okay, and so once all these things come together, right, you can actually put together a calculation that looks like this. Okay, so you can see the upstream turbine, right, is generating this tip vortex. There's quite a bit of turbulence that gets shed off the tower. Okay, because this guy operates in an atmospheric boundary layer with turbulence around, right? These vortex rings don't persist. Okay, they break up pretty quickly. Okay, but then it looks like they recombine further downstream. A very interesting observation we made, and we've seen it in some of the other calculations by other researchers, right? And then all this mess goes and hits the turbine in the back. Okay, right. So we're able to capture that phenomena, right? Quantitatively speaking, right? We can track the tip displacement, right, of the upstream turbine, right? And you can see that you can clearly see the effect of stratification, right? And so you see a lot of displacement in the inversion layer, right? When the blade is kind of in the vertical direction facing upwards, right? As it goes around the circle and goes down, it goes into the regime of slower flow, right? And then the deflection decreases significantly, right? As you can see. Right? And so you have this sort of a cyclic behavior and the corresponding loads, right, and the corresponding structural response and the stresses that you need to take into account when designing wind turbine blades for this type of operation, right? And it's these type of advanced calculations that are really shedding light on this more nuanced behavior. Okay? This is aerodynamic torque, again, comparison between the rigid and flexible blades, right? And you can see that with the flexible blades, you can pick up additional sort of deformation modes, right? There's a slower mode here, right? And also high frequency torsional mode that we see in a lot of these calculations. Again, that's not possible in a pure sort of CFD simulation of these systems, right? This is the air velocity profile, right? As we're moving, right? So it's very clean before it hits the first turbine, gets really disturbed, okay? Takes a while for it to recover, right? So about half a kilometer, right? You get something like this. You get a clean profile overall, but you clearly see the velocity deficit, right? That comes from the upstream turbine here, right? And then that profile with that velocity deficit hits the turbine in the back, okay? And then again, the boundary layer gets disturbed, but the result of this velocity deficit is clearly seen in this figure, right? So if you look at the time history of the aerodynamic torque for the upstream turbine, which is here, and the downstream turbine, which is there, right? You can see a drop of about 10 to 15%, okay? And so if you take the aerodynamic torque and you multiply by the rotational speed, this is the amount of power, right, that a turbine is able to capture from the surrounding air, right? And you can see that the downstream turbine captures 10 to 15% less power and will likely generate a smaller amount of electricity, based on that drop. So we're actually capturing that effect in these calculations, and these are the numbers that are reported for some wind parks. So we're not completely off. Okay. And of course, next challenging step: how do you go offshore? And it's just a calculation we did of a floating wind turbine. And the entire structure is built using isogeometric shells here. It's actually moored to the seafloor using cables, also isogeometric cables, and it's immersed in this air-water sort of two-phase, right, or a two-fluid framework where we use a level set technique to distinguish between the two fields. But again, just showing where this research will likely go. Okay. All right, so let me talk about the second case. Okay. And it deals with FSI analysis of long-span bridges, again, where some of our methods are at least trying to make a difference in this type of applications. Our collaborators are from NTNU in Norway. They're carrying out a lot of experimental analyses for this type of applications, and this has been really a fruitful collaboration over the past couple of years. Okay, and then the challenges are, right, and these are very long bridges. Okay, so these are not typical designs. Especially in Norway, you have very specific conditions in these fjords. Oftentimes you get very strong winds, right? And, because of the different environmental conditions, right? And the different designs for the bridge decks themselves, again, you have to, develop a good understanding of how these long span designs react to wind loading, what are the conditions for flutter, for buffeting, and so forth. And so this is kind of driving a lot of that, these questions are driving a lot of that research. Okay? And there are many ways to do flutter. Okay, oftentimes it's done by forced vibrations. Okay? And what that allows you to do is determine the so-called aerodynamic derivatives. Okay, you carry out prescribed motions of the bridge deck. Okay, you can do pitching and heaving motions. Okay, extract the lift and moment coefficients, right? And write down sort of a fairly simple dynamical system for this. Okay, and the coefficients of that dynamical system will depend on the so-called aerodynamic derivatives, right? That are extracted from typically experimental, from the experiments, right? That are carried out in wind tunnels for sort of a lab scale and then kind of upscale to the full scale. But again, there's no reason not to do this computationally, okay, as I will show you. And in this case, several wind velocities and vibration frequencies are run sequentially, okay? So this is a heaving case, right? This is our calculation. You see the design of the bridge deck here, right? And I want to draw your attention to is sort of the type of flow that you're seeing, right? So first of all, this is a three-dimensional calculation. The only way you're going to be able to capture this space and time dependent turbulence, okay, is to do these calculations in 3D, right? In 2 dimensions, these turbulent structures do not exist, period. Okay. Right. This is a comparison of a lift coefficient between the wind tunnel data, right, and dashed line here, right, and calculation that's actually done using isogeometric analysis for fluid mechanics. So the entire domain is parametrized using a volumetric spline, okay? And you do get higher quality solutions that way. Okay? This is the raw signal, and then this is the filtered signal that lines up very well for the lift coefficient for the heaving case. Okay, this is pitching. Okay. Now you can see that things get a little bit more complicated from the fluid mechanics point of view, okay? And again, this is the a lift coefficient, right? Comparison of the IGA simulation and the test data, right? And so as you can expect, the frequency lines up quite nicely, right? But there's some discrepancies in the amplitude of the pitching, okay? We'll come back to that point later and to explain why that is, but overall the agreement is not so bad, okay? And so then you go ahead, right? So this is the damping and stiffness matrices, right? That come out of the simple sort of dynamical system approximation, and they're populated by these are the H's and the A's of the aerodynamic derivatives here, right? And so these are the aerodynamic derivatives, right? As a function of the reduced velocities that are extracted at for these forced vibration type calculations. The red are the experimental results and the blue are the computational points, right? You see that the overall agreement is not so bad. I mean, there's some suspicious behavior in the A4 and the H4 that are related to pitching motions, right? That are, you can actually see some of the issues cropping up here. But overall, it's pretty good and certainly a lot less expensive to carry out the experiments, especially, the calculations, especially if you're planning to test, multiple deck designs, okay? Now, why, you don't need to limit yourself to forced vibrations. You can do free vibration, right? You can simultaneously solve for the fluid mechanics, right? And the motion of the bridge deck that become your problem unknowns, right? So these are the calculations of the bridge deck and the still wind, with just maybe a little bit of velocity, comparing the wind tunnel and simulation data, right? So we're capturing the decay very, very well, okay, in the heaving amplitude and the pitching amplitude here, right? This is the calculation at 50% flutter speed, right? Again, comparison of wind tunnel and simulations, right? And we're actually capturing the decay of the heaving amplitude very well, of the pitching amplitude very well, and you can see that the heaving decays much faster than pitching here. Okay? This is the experimental setup, right, at NTNU. Right? So they put this thing in a wind tunnel and they send the wind this way, and they find that these are the reduced critical velocities and frequencies at which flutter occurs. Right, and our calculations give very close numbers. Okay, so we're actually able to predict the critical velocity and frequency for this bridge deck just by doing calculations. Okay. Now the next topic, right? Of course, in reality, nothing exists in uniform inflow conditions, right? Even in the wind tunnel, there's a certain amount of ambient turbulence that is present, right? And often you put in screens in order to sort of control, how much turbulence you do want in the air, right? To sort of mimic the real conditions. And so we needed to bring this into the simulation somehow, and there's quite a bit of work of doing this, and basically doing a synthetic turbulence and then trying to feed the synthetic turbulence of prescribed turbulence intensity at the inlet. We decided to do something different, okay? And we decided, again, to use our multi-domain capabilities, right? To first develop a turbulent flow offline, okay? So what we did here, right, we did an offline calculation of a three-dimensional turbulent channel, right? With wind speeds and dimensions that correspond to that wind tunnel, okay? The parameter that we control is the turbulent Reynolds number. Okay. Once we developed that flow, right, we went and we subjected the bridge deck, and in this case, a simple rectangular deck, to turbulent inflow, okay? Just to see what the effects are, right? And you see, again, this is just a cut. This is, again, a three-dimensional calculation, right? And so the bottom figures are showing something interesting. On the left, right, you see zero turbulence intensity, meaning uniform flow, right? We compute for a while, we compute the mean flow, right? And you see, right, the size sort of the recirculation zone, right? And the recirculation zone, almost, I would say about 2/3 of the deck here, right? For no turbulence. As soon as you introduce some turbulence in the flow, right, you compute for a while, right? Look at the size of the recirculation zone on average. It's a lot less, right? It's less than half, okay? And so this is precisely what helps explain the inaccuracy of the pitching moment, right? Because this dictates the pressure distribution over the deck, okay? And unless you have some turbulence in the free stream, which exists, in the wind tunnel and in reality, you have no way of capturing the right distribution of pressure, and there is no way of capturing the moments accurately, okay, for this situation, okay? So then we went back, right? We fed the turbulence in, and we recomputed the aerodynamic derivatives, okay? And lo and behold, right? If you look at H4 and A4, right? By introducing just a little bit of turbulence into the surrounding air, gives you much more accurate pitching response. Okay, so I think this is sort of a very another important observation and the important finding of this work. And then you can go beyond, right? I mean, you can see a situation where supposedly, you've designed this bridge, and then you have some, wave conditions, right? You have a wave, right, that comes in. And this could be like 100-year wave, which is, 2-3 meters in amplitude, comes in at about 10 meters per second, right? And so as that wave goes under the bridge and you have strong wind, okay, what happens to wind loading in this case, right? So with the Norwegian colleagues, we sort of set up this scenario, right? Again, on a moving grid, right? So what you can do, you can take the bottom of your computational domain, right? You can assign a wave profile and propagate it, okay? And so, right, so the surrounding, air feels the presence of the wave, okay? So these are the conditions, right? At the mean water line is about 12 meters away from the deck, right? At the peak, right, the peak of the wave will be 10 meters, right? So you can see, so this is the wave amplitude, okay? And you can monitor the moment coefficient, right? And so if you don't have any water, right, you just do, pretend there's air everywhere. This is your moment coefficient here, right? If you put the mean water line, right, and feed in this corresponding boundary layer, right, you can see that the moment coefficient changes. Again, this is a non-symmetric deck, so you should expect some moment there, right? So there's a fairly significant influence, just the presence, right, of the water and the presence of that boundary layer, right? But if you send the wave in, right, in the beginning, right, when the wave is far away, your moment coefficient clearly aligns with the mean water line, right? And then as the wave gets closer, you see a significant dip and then a significant growth, and then you go back to the mean response, right? And so again, these type of calculations, you can see that the distance between the trough and the peak, right, is about twice the size of the mean, okay? And again, these are some of the loads that you may want to take into account when trying to design resilient long span bridges. So again, this moving domain sort of fluid structure interaction can help you in these type of designs quite a bit. Okay, and let me close very quickly with the application that we've been developing with my group members and collaborators from UCSD and I'm at Brown now on the air blast fluid structure interaction. And here we're coupling isogeometric and mesh-free methods. Okay. So we've been working on the immersed FSI framework that couples large deformation elastic solids, compressible viscous flows. Both are in the weak form, okay? And I have a priori strong coupling even for explicit time integration. Spline-based isogeometric analysis is used to the background, and it's used to approximate fluid and solid fields, okay? In the absence of the fluid that I showed you in the beginning of the presentation, the formulation reduces to an MPM or a material point-like method, okay? The good thing is that because of the isogeometric methods and smoothness, you have a continuous strain rate, okay? So as the particle go from one element to the other, there's no discontinuity in the strain rate, there's no discontinuity in the stress, and you get overall stability and accuracy as a result, okay? For the foreground, we use sort of a mesh-free method like in RKPM, which is very nice for to be able to fragment and disintegrate the solid. Okay? And so with this, we can carry out calculations like that, right? Where you set off, this is a two-dimensional calculation, you set off a blast, right, in the room, and you can see the blast wave, going and interacting with the objects, and the objects contact each other. And so these are some of the advantages of using these immersed methods, that you don't really need to do anything special for contact and so forth, right? Right, and you can see that the gaps are naturally created or removed between the objects, and air can very naturally enter these gaps. Okay? And so this is some of the difficulty that if you try to do everything Eulerian or everything Lagrangian, right, you see the weaknesses. And here we're really combining the best of both worlds. Okay, this is an example with some experimental data. It's a blast wave affecting a panel. Okay, so a shock wave comes and sets the panel into the vibrating motion. So it's a 2D example, right? And this is a tip displacement as a function of time. And this is a pressure at a given pressure probe in the domain. And there's some experimental data, and it looks like we're capturing the natural frequency very well of the vibrating plate. And we're capturing the pressure, the first shock, and so forth also pretty well. Right. This is an example of going to a more advanced modeling for the solid part, where we bring in the so-called phase field models to model fracture, okay? And this is a blast that's set inside a rectangular container, right? So as the blast wave reaches the walls, right, the stresses that are induced in the solid are so high that it starts to fracture, okay? The fractures are driven by phase field, right? They emanate from the regions of stress concentration, travel outward, right? And as you can see, once the solid fragments and starts falling apart, right, then you see the areas open up naturally, right? And because the solution lives in the background, they get filled up, right? I do have the air discretization there, right, in order to continue running the coupled problem. Okay. And finally, let me conclude with this image here. It's a three-dimensional calculation of a cone blast on top of a concrete block. Okay. So what we're tracking here is the evolution of the solid here, right? The red is actually right, we're using a concrete model here that uses damage, right? So the specimen starts out as pristine, and you can see the damage growth is sort of indicative of the formation of these 45-degree shear cracks, okay? And in concrete, you see the formation of a crater, right? All the particles are flying, right? And with the blue particles here, we're actually tracking the explosive itself. Okay, so in this calculation, we're coupling air, concrete, and the explosive, so you can have the flexibility like this. Okay. So there's still a lot to do here, but in the interest of time, let me conclude here. I'd like to acknowledge my sponsor, and thank you very much for listening.
Okay, so we're back live with Yuri now. And we have a few questions that came up during the talk. And so let me go ahead and begin by, first of all, thanking you, Yuri. That was an excellent presentation. Covered a lot of ground, particularly toward the end. And so I'm sure we have some thinking we have to do about where applications like this might be especially beneficial. So I'm going to start with first question. It says, what software did you use, and is it freely available?
Okay, Chris, yeah, let me take this one. The software is essentially a research software in my group at this point.
Yeah, I'm sure.
It has been sort of, shared with colleagues, but, typically those that are kind of in a close proximity to the group. Several joint proposals were written for, research topics, and I guess Chris and I, tried to go after some NSF funding. We've also used it in sort of, industry and some kind of SBAR, STTR supported projects, but it's not a software that is freely available or that you can easily license. But I'm certainly, looking forward to, other collaborations and other applications where maybe we can develop more customized solutions. Because, every time a problem comes, yeah, the software is there that can do basic things, right? But for example, I showed several multi-domain calculations, right? And as we were tackling that challenge, a lot of these multi-domain techniques had to be basically developed on the fly, okay, in order to carry out computations like this. So it's not anything that is commercial grade, or it's not, Fluent or COMSOL, or,
Well, let me put it maybe some different terms, if you don't mind.
Right.
Think defense contracts that have different levels of applications. So where would you say this is on a T1 to, higher level?
This is somewhere in 6.2.
Okay. So we look forward to moving that towards
towards
other end. And
6.3 and 6.4. Right. Me too.
Yeah.
And again, there's there's the sort of the fluid mechanics part, and you saw the first two applications really were kind of this milder sort of, maybe I would say, environmental type flow regimes, and compressible assumptions are okay. And it's got some issues that you got to tackle on the incompressible flow side. Certainly, high Mach number compressible flows when it comes to blast, and is a completely different thinking and philosophy that goes into development. And these
you're solving very complex problems, so I'm sure it will take a lot of effort to think through how each application can be adapted to make it computationally efficient. All right, second question here. Can you couple the fluid part with a discrete element model for the solid like DEM, discrete element method?
Absolutely. And I think there's a lot of interest in these type of applications now, right? People are looking at sort of, erosion problems, right? Water comes and in many cases you do want to go to a discrete element type approach. And what's becoming more popular, and I think there's quite a bit of research, is in these immerse type methods, okay?
Mm-hmm.
Where you would overlay your discrete element model or discrete element grid, and you're allowing these discrete elements to move. You overlay it on top of a fixed type domain where you solve your fluid, see? And then
But
you
I
would
guess
use some kind of a coupled technique to do both. So it'd probably be very similar to the last part of what I showed you. Right.
Yeah,
I
with
think
the
that would
chairs
be
and
a
the
way.
room and that
That's
sort of
right.
thing.
This would be a way to bring in discrete elements into the coupled FSI framework.
All right. And I suppose there's still time to bring in additional questions if somebody wants to post it. But in the meantime, let me just ask you a resilience type question. So now you have these incredible tools to capture the physics that's maybe hard to actually see with ordinary tools. And so you're able to get an enhanced view of these things that actually occur. So my question is, in the context of resilience, we want to get an appreciation, a measurement, an assessment tool to show that we are actually able to identify the time element in terms of amount of recovery, how much loss, how much, and in one of these large scale, for example, the large scale bridge, can we demonstrate that if you don't do some of these things, your resilience will be at one level, whereas if you do these things the way you're proposing with your techniques, you're going to pick up not only the ability to design better, but you're going to make them perform better. So have you given some thought to how the works, the outcomes of your simulations can actually be applied to these resilience ideas?
Right. So I think, well, let's take a bridge as an example, right? What happens on the experimental side, right? There's quite a bit of work, but everything is sort of taking place at the wind tunnel scale, right?
Mm-hmm.
So then we're talking, 1/50, 1/50th or so,
Mm-hmm.
right, of the actual scale, and there's not much more than you can do, I think, experimentally. So then where the computational techniques come in, and this is kind of where we are with that application, is you would first develop what you need on the computational side and sort of anchor it, right, or ground it to some of the experimental data that you're picking up from these lab scale tests, okay? And then the next step, you can probably upscale the computation. Again, it's just a matter of changing dimension. Of course, some other questions come in. Can you really resolve things at that scale, right? But, provided you can, right? Then you do have a tool, okay, that offers some accuracy and the ability to predict behavior at full scale, right? And there you can start talking about, solutions, right? You would want to, for example, you would want to design, some kind of maybe additional structures on your bridge, right? To take it away, from the natural frequency of vortex shedding, right? From the natural frequency of the deck vibration somehow. You see what I mean? And yes. These type of experiments, right? Computational experiments you would do at full scale. I think this is where the resilience comes in, that you can probably turn the designs around, somehow. I wouldn't say fast. Again, these computations are not minutes, right? I mean, they run overnight or a couple of days usually, right? But still not something out of the range of something that you can apply at the real scale. I think if you can do some structural design, maybe bring in some shape, your geometry optimization tools, you can probably go far as creating resilient designs. Chris, does that answer?
Well, I have maybe a follow-up to that, but there's been another question posed. Thank you for this presentation. This is from Amit Avad. What kind of changes in the modeling and coding are needed when working with different applications?
Well, I mean, if you let's say if you're working with turbines or with bridges, I think a lot of the core things are there, right? If again you think of finite elements, you think of the element types, quadrature rules, assembly of force vectors, that you don't touch so much. Where a lot of the effort comes in is implementing a new type of boundary condition, right? Or building in some additional things in order to be able to do domain coupling and things like. So this is where a lot of the efforts go, not into the core parts, right? Of course, when you bring in solids, you spend a lot of time in constitutive modeling. I think that reality is not going to go away anytime.
Yeah, I thought your
anytime soon.
Use of the composites in the turbine plate was
right,
rather,
that's right.
rather what are you going to say, ambitious activity. But okay, and I forgot to mention the previous questions came from Mohammed Al-Nagar. Al-Nagar. I guess returning to the how to use this for resilience, improving objective resilience. Obviously, you're improving the ability to capture the behaviors. I think the issue is at what points do we start to go to this level of enhancement when we are maybe either in planning stages or maybe looking at emergency response problems, recovery from large-scale disasters. So can you see this being scaled up to include, say, the entire say bay that bridge was located in, so that you could start to see the effect overall, not just on one facility, but is that exceeding the ability of our computing at these days? Or?
I think the appetite for computing will always outgrow the hardware and software capabilities. I think that statement is true and will remain true. Well, the term that's floating in the at least you see a lot in the DoD side is what digital twins, right? It's been around for I don't know 10 15 years, and I guess the idea is that you sort of attach some kind of digital counterpart to your system, whichever way you define it, right? And it kind of lives with it, right? And so, and you use a lot in the maybe initial stages, the design stages, right? But then you transition to something that is able to maybe monitor that structure, right? Update that model. Okay, so for example, you've incurred a certain amount of damage, right? So then you need to go and maybe reduce, stiffness here and there. It's a kind of a trivial thing, but right, and then you just have this tool or a set of tools that kind of live with your structure throughout its life, and then hopefully at not just at the design stage, but at least in the operational stage, you can sort of query things and you can run some predictions to see where that structure is going to go. Right.
So with the isogeometric
probably
part,
I don't know if universal, right? This is, well, you can do any bridge. My feeling is, fluid equations are not going to change, right? Probably the way you describe your solid model, a structural model will depend on, your preference for, different element types and how deep you want to go. You want to go 3D continuum or you want a simpler representation. Once you've made these choices, okay, then you have something that works with that particular structural system, and then you can make changes and make things predictive. I think the framework covers many things, right? But when it comes to the application, you probably want to sort of have a collection of tools that is suited for a given structural system that you're studying. I think that would be a more practical solution to try to cover everything, with one methodology. Right?
Okay, we have one more question. Thank you again for the great presentation. This is from an anonymous attendee. Can the IMGA immersed method capture solid material nonlinearity while having turbulence for the fluid part?
Absolutely. And this is where a lot of the research is, it's a question of, how you formulate the problem, right? Once you solve it, you see, as with everything with FSI, right? If you have a good solid, you have a good fluid, right? I think most of the battle is won. right? Then you want to make sure that your coupling procedures are appropriate, right? That you do have a coupled system that satisfies in some sense the kinematic and traction constraints. Once you have that, right, then capturing nonlinearity depends on how good your solid mechanics formulation is. So I don't think
So
there's
the
a
short
fundamental,
answer is yes.
I don't think
in
there's a
principle, but-
fundamental difficulty in doing that.
Okay.
Right.
Okay, I think maybe at this point we may want to start to let our closure begin. But any final comments you want to make before we open it up to some other folks here?
No, Chris, I think this is it. Again, it's been great to be able to deliver this lecture, and the questions are quite stimulating. And I often get questions about the availability of software, and it is really motivating me to do something about it. So,
okay, well,
thanks
thanks
very
so
much.
much for you taking the time to do this and preparing such a wonderful lecture. And I will say that for those listening, the whole presentation has, including the live part, has been recorded. And so this will be posted on the EMI website very soon. It's not in my hands at this point, but I know our technical staff are going to be doing everything to get it to EMI promptly. So since registration process took place, everybody will receive eventually when that link is available to do that. So I do want to do some acknowledgements here, and we have a representative from both the EMI committee and the Disaster Resilience Constellation on the panelists group. So first of all, let me acknowledge Dr. Mohammed Atouni. He is really the brainchild. This is the brainchild of his work, the committee's work. And so Mohammed is available if there's any questions for him, or for Mohammed, if you would like to say a few words. You would just need to unmute yourself and go ahead.
No, I'm fine, Chris. I would just leave it up to everybody else. Thank you.
Okay. And also, we have Stephanie Otts from our Disaster Resilience Constellation at the University of Mississippi, who has graciously done some multitasking here. So Stephanie, would you like to say a few words about the constellation?
Yeah, so yeah, as Chris mentioned, I'm co-chair of our Disaster Resilience Constellation. It's part of an initiative here at the University of Mississippi to support and encourage interdisciplinary work across campus. And so I'm an attorney, and it has been really interesting to learn and work more with the engineers across campus. And so I just wanted to thank the presenter and EMI and Chris and everyone who had a hand in organizing this. I think it's been a really good event to be supported, in part by the Constellation.
Okay. Thank you, Stephanie. Let's see. I want to acknowledge our technical staff here from the Office of Research, who has put together the promotional materials and also managed the live stream of the live webinar. First of all, we have, well, let's see, I'm just got to check and see who's still online. Well, we have Kendra Sampe, who has been instrumental in keeping the overall flow of all this work going. We have Brian Hopkins, who's in our supercomputing center. And so we also have Brad Palmer, who has been managing some of the webinar features. So thanks so much for all of y'all's help. And at this point, I guess, Amar, would you like to say a few closing words, or are we good to go?
Well, thank you very much. Well, we seem to be having trouble with the video, but in any case, this was a fantastic lecture. Thank you so much to Professor Bazilevs and all those from the University of Mississippi who had in hand in organizing and hosting this very nice event. Thank you. And the video recording will be posted in next few days. Thank you. Have a good rest of the day.
Thanks to all our participants. Please feel free to contact me if you have any questions. Yuri, thank you so much.
Thank you, gentlemen. It was great. Yes.
All right.
Thank you.
So, I will say, feel free to contact me if any of you who are listening, if you want to learn more about any of the activities we're doing. Also, Dr. Otuni, I'll be happy to forward anything on to him. So my email address is cvchris@olemiss.edu. So look forward to hearing from y'all. Please let us know how you enjoyed the lecture. All right. Take care, everybody.